Hi, everybody. Today we are starting our new chapter and we are learning about how lines can intersect with planes in R3 and also how lines can intersect with other lines in R3. And so we're looking specifically at the vector equation of a line and the Cartesian equation of a plane. Okay, so first of all, let's talk about the three different ways that a line can intersect a plane. The first option is that there's one intersection. So that would be like you can draw a line coming up, and then it would be underneath, and then hitting at this point and continuing on. So we label this L and this pi, and then this would be the point P of intersection. So it would intersect at exactly 1 point. Okay, now another option is that the line is parallel to the plane. So here we have our plane, and we can draw our line above here. There's our L, and then we can show that they are perpendicular. Okay, so the normal to the plane then would be, show it down there. The normal to the plane then would be perpendicular to the line as well as to the plane if the line and the plane are parallel. And finally, there can be infinite intersections if the line is actually on the plane. Okay, then there would be infinite points of intersection. So now let's go to some examples to show each of these cases. Okay, so in this one, we have our line. Notice it's in vector form, and our plane is in Cartesian form. So we're going to put the line into its parametric form, so splitting up the x, y, and z. So x is equal to 3 plus s, y is equal to 1 minus 4s, and z is equal to 2 minus 8s. Okay, so that's a 2, sorry. Make it look like a 2, not a z. All right, so now that we have the three parametric equations, we're going to actually put them in place of x, y, and z in our Cartesian equation, okay? Because that allows us to, again, find the point of intersection where the x's are the same. So we have 4, and then instead of x, we put 3 plus s, because that's what x is, plus 2, bracket 1 minus 4s, and then minus z, so 2 minus 8s, minus 8 equals 0. Okay, so now we have this equation, which only has one variable, so you can actually solve for s. So if you go ahead and do that, you get s is equal to negative 1. So now we just substitute that parameter, s equals negative 1, back into the parametric equations, and that will give us the point of intersection. Okay, so x equals 3 minus 1 is 2, y equals 1 minus 4 times negative 1 is 5, and z equals 2 minus 8 times negative 1, which is 10. So 2, 5, 10 is the single point of intersection between this line and this plane. Okay, now we're going on to another example where something else will happen. Okay, so find the point of intersection between, now notice they're already in parametric form, and this plane, which is in Cartesian form. So again, we just do the same process where we put our parametric equations into the Cartesian. So fun, right? Just, I don't know. It's nice when we can just solve for t, just a single variable. Imagine that. Okay, so what happens here though is that you get, check this out, you get 4 plus 2t minus 10 minus 10t plus 9 plus 8t minus 6 equals 0. So notice that the constants all cancel each other out, and also the coefficients in front of t cancel each other out. Sorry, my bad. The constants don't cancel each other out. The constants get to negative 3, Okay, so what you result in here is a 0t equaling -3. Basically, the coefficients, that's what I should have said, the 2 minus the 10 plus the 8 go away. So t essentially goes away. But we write it here with a coefficient of 0. And then the constants will get to 3. So when you move it to the other side, it's -3. Okay, what this means is that there are no solutions. Okay, think about why it means that. Because no matter what I put in for t, 0 times that number will never equal -3. Just not happening. So that means since there are no solutions, it means that the line and the plane are parallel. Okay, because that is what happens when there's no solutions. They're not intersecting ever, they're parallel. Okay, method number 2 of either proving this or verifying this for those communication questions would be showing that the normal of the plane dotted with the direction vector of the line equals 0, okay? Because that would mean that the normal of the plane is perpendicular to the direction vector of the line, which means that the line and the plane are parallel. So that's a fun little added understanding for your old noggins. Okay, the next one, find the point of intersection between this line and this plane. Okay, Mrs. Weens, we know what we're doing here. Why are you making us do this? Well, I'm just going to show you different results and what happens, okay? So bear with me. So you put in your x parametric equation, which is 3 plus 14s, and then plus your y, so -2 minus 5s, and then plus 3 times your z, so 1 minus 3s, okay, -4 equals 0. Now, when you solve this, you get 0s equals 0, okay? The constants cancel each other out, and the coefficients on s cancel each other out. So think about what this means. This means that there are infinite solutions. Yay! Why is that true? Well, no matter what you put in for s, it's always true. 0 times everything is always 0, any real number. So there are infinite solutions, which means that the line lies on the plane. How exciting for us. Okay, now another thing you could check is that the normal of the plane crossed with the direction vector of the line equals 0. Okay, that would also verify that there are infinite solutions. Okay. Last one, find the point of intersection between this line and this plane. So this is just to show, like, if you just have a basic plane like this, how do you do it? So this is, think about it, parallel to the YZ plane, and x is always -3. So the line will intersect the plane when x is equal to -3. Okay, that has to be what x is for these to intersect. Okay, so what we do then is we take our parametric equation that represents x and we set it equal to -3. Okay, in that case, t equals 5. So that is the parameter that gives the desired x value. So now we can throw that into y and z to find out what those values are, and then that gives us our point of intersection. You know, we should really make these z's look like z's and the 2's look like 2's. I should really loop them. Gets a little annoying. Okay, so -3, 14, -6. That is the point of intersection. All right, so that is intersections between lines and planes. Now we can talk about the intersection between two lines. So you might be like, well, Mrs. Weens, like, we already know all about this because you taught it to us in grade 9 and you did such a good job. It's too easy for me. Well, now we're in R3, folks, so there is a fourth case about intersecting lines. So either they have one point of intersection, so they're not parallel and they intersect once, or they have infinite points of intersection, which means they're coincident, so basically one on top of each other, the same line. Those are the two ways they can intersect. We're used to that. But now, what about non-intersecting lines? Either they're parallel or they're this thing called skew lines, which basically means that they're not parallel, it can be like this, but they don't ever cross. So this is only possible in R3. I have a friend whose last name is Skew, and he's a math teacher, so I always make fun of him for this. These are the kind of jokes you make when you're math teachers. We're really quite cool, let me tell you. Okay, so when determining the intersection of two lines, you always want to check if the direction vectors are scalar multiples, because if they are, you know it's either case 2 or case 3. So that automatically omits that. So always check for that first. Okay, so I'm just going to do one example like this, and I believe that it is enough to get you guys where you need to go with the rest of the work. Okay, so the first thing you check these two lines is if they're parallel or coincident. Well, they're not, because check out the direction vectors. -1, 1, 4 cannot be written as some scalar multiple of -6, -1, 6. It's just not happening, where k is in the set of all real numbers. So that means that I know that these lines either have to be intersect once or they're skew. So I've already narrowed down my options by half. So now I'm going to convert each one to its parametric form. Now the best way to keep this organized is to have a list for line 1 and a list for line 2. Okay, you can even make a little chart if you feel like being snazzy. Who doesn't feel like being snazzy every once in a while? I'm just making them parametric equations all day. All right. Okay, line 2, 1 minus 6t. Almost should have had these pre-done for you, because you guys, this is old hat to you by now. Do you guys still say that, old hat? Does that make me really old to say that? All right, okay. So these are the parametric equations. So think about it. A point of intersection is when x is equal to x, y is equal to y, and z is equal to z. Just by definition, that's what a point of intersection is. But we only have two unknowns, s and t. So we only need two equations to solve for those two unknowns. So basically what we're going to do is I'm just going to choose x and y as a system. Okay, solve for s and t. That will give me the parameters that will make x and y equal. Then I take those two parameters, and if they make the z's the same point, we got our point of intersection. And if they don't make the z's the same point, it's skew. Okay? So that's what we're doing. Okay, so we just have a linear system. So I'm going to make x1 equal to x2. Okay, so that's -3 minus s equals 1 minus 6t. And then I'm going to set y1 equal to y2. And then that's 1 plus s equals 4 minus t. Okay, so then we go ahead and solve this system. So you can use elimination or you can use substitution. I hope you trust me that I get from this that t equals 1 and that s equals 2. All right, so now I'm going to sub these back in. So if x1, y1, z1 equals x2, y2, z2, then they intersect at that point. And if not, they're skew. Okay, we know that x1 and we know that the x's and the y's will be equal because we use those to find the two parameters. Okay, so that should be no shock at this point. What we're really looking at is our z's. So if you put 1 in for x, get -3 minus 2 for this one. Sorry, s, that's s. So that gives me -5. Okay, I'm putting in the parametric equation. Again, line 1 is I'm putting in S, so I'm putting in 2. So 1 plus 2 is equal to 3. And then Z, I get 4 plus 4 times 2 is equal to 12. Okay, so now for the line 2, I'm putting in T as my parameter. So 1 minus 6 times 1 is -5. So far, so good. 4 minus 1 is 3. So far, so good. So here's the big test. Drum roll, please. 6 plus 6 times 1 is 12. Yay! Okay, so that just means that -5, 3, 12 is the point of intersection where they intersect. Okay? If that final point had not been equal, you can conclude they're skew lines as long as you've already shown that they're not parallel or coincident. Okay, one last final thing, and this is just getting us kind of set up for solving a bunch of lines together. You'll see it's a lot of fun. Okay, so this is basically just getting used to the vocabulary of what elementary operations and equivalent systems are. So remember, a system of linear equations is a set of one or more linear equations. So that's what I mean by a linear system. And a linear system can have 0, 1, or infinite solutions, which correspond to the point of intersection. So an equivalent system is just two systems of equations that are equivalent if every solution to one system is also a solution to the second system. So we did do this briefly actually in grade 9. So there are 3 elementary operations that create equivalent systems. So one is to just interchange any pair of equations. So let's pretend I give you the linear system 2x plus y equals -9, and I call that equation 1. And then I gave you the equation x plus 2y equals -6, and I call that equation 2. So this is a linear system. It has a solution, okay? So one elementary operation is to honestly just switch the 2 equations. So x plus 2y equals -6, and now I'm just going to call that equation 1, and 2x plus y equals -9, and I'm just calling that equation 2. Call me crazy, but that's still an equivalent system. The solution is still the same. Okay, now another elementary operation is to multiply an equation by a non-zero constant. So in this case, I'm going to multiply -2 times equation 1. And that would give me -2x minus 4y equals 12. So now I'm going to call this equation 3, this new thing. So -2 times equation 1 gives me a new equation, equation 3. So the last elementary operation is you add the non-zero multiple of one equation, so this, to the second equation. So I'm going to take 3 and I'm going to add 2. So -2x minus 4y equals 12 is added to 2x plus y equals -9. Okay, so you add these together, you get -3y equals 3, which gives you y equals -1. You can put that back in, you get x is equal to -4. So the solution to this linear system is -4, -1. Right now you're probably like, Mrs. Weens, that's just elimination. We learned it in grade 10. Yeah, it is. It just has a different, we just need to use the term elementary operations and equivalent systems because we're grown-ups now. Okay, so that's all it is. So when it comes up tomorrow or in the next video, just realize that that's all it is. And just realize that each time we create a new system, if it's equivalent, then the solution is the same, okay? So if a system has one solution, we call it consistent. But if there's no solutions, we call it inconsistent. So we will be using that vocabulary throughout the unit. All right, guys, you guys heard the bell a little while ago. It's lunchtime. I'm hungry. Gotta go. Thanks for watching. Hope you learned lots.